Hello everyone. This is a CS50, a Section 6 operating system, week number 12, Wednesday lecture video. Today I'm going to cover the file worksheet that is posted on Blackboard, questions number 1 through 5 out of the total 7 questions. Next week, I'll cover week number 13, I'll cover, I'll finish the worksheet, questions number 6 and 7, and then I'll do the lecture file lab. So let me get rid of this one, bring in the Blackboard. So here's a week number 12 and 13 together, and you can download this file worksheet. Uh, you should see this worksheet questions. As I mentioned, here's 1, 2, 3, 4, 5, 6, 7, but I'm going to bring up my notes. So here's my notes, but before I start going over the questions and answers, I want to set the context for what we're talking about today. As the title states here, the topic for this chapter, the week number 12 and 13, is the files. So far we talked about the RAM, where the processes are, and these processes come from the secondary storage device, right? And then so we talked about how to organize the RAM, how to process the processes, and then how to organize the SSD or the secondary storage device. But in here, there will be files here, and we're talking about these files themselves, not necessarily the storage device. But they're sort of related, but we're just exclusively talking, we're focusing on the files themselves, okay? So let's do the first question here. Let me make it a little bit larger. So the first question is, what are the 3 common methods for file allocations? There are three common file allocation the methods, and the questions are, what are they? What are their advantages and disadvantages? And which one is the best? What are they? They are continuous, linked, I should say continuous or contiguous, either way, and then indexed. Let me show you how they look like, and then you can come up with your own advantages and disadvantages, because it should be pretty fairly obvious, and I want you to put it in your own words. Okay. So the first one is called the contiguous or continuous. In other words, files that are stored they're stored in blocks, and for a given file, they are stored in continuous blocks. So if you look at the file directory here, this directory has the file name, where it starts, the starting block number, and how long it is. So the file called count starts at block 0 right here, and then it has length of 2. Here's 1, and here's 2, and they're contiguous, right? And then let's say the mail file that starts at number 19 has the 6 of them. So 1, 2, 3, 4, 5, 6. So as you can see, they are continuous, right? So this is uh, um, the blocks are contiguous. I guess this could, I don't know, maybe this is not very helpful, so let me get rid of that. Okay. Anyway, so hopefully that makes, it's pretty simple and straightforward. Obviously the advantage is like it's easy and fast to read, but the disadvantage would be if you need to expand them. So let's say, for example, number 14, let's see here, well, even this guy here, 28, the list file, and it is a length of 4, but after you're reading it, if you need to uh, store a increased file size, it can't go anywhere, right? So like another one that starts at 19, mail file that starts at 19 and ends at 24, what if you, after you read it, and then you added a lot of stuff, and so you need 4 more blocks when you're saving it, but there's only 3, and so you can't do it anymore. So Reading is quick and easy and brief, but the writing is really the culprit. The next one is called the linked, and the file blocks are linked, or the file parts are linked, right? So the directory has, in this case, there's only one file listed in the directory. The file name is Jeep and starts at number 9, just as an example, right? And then it ends at 25. But after it reads in here, um, it'll have the not only the data, but it'll have the pointer of the block number. So it goes to 16, and then after it reads it, after it is completed or whatever, reading or writing, it'll have a next block ID and just kind of traverses here. So 10, 25, and when you get to the last one, this will have the pointer of negative value. And as you can see from the block number, there is no such a place called negative number. So it will know that it is the end of the block. Not an end of a file, but end of the blocks for that file. So this is a linked block method. Advantage would be to, you could specify where to use the next block that is available, so it's efficient use of the free available blocks. But the trouble is, there are too many pointers, and if any one of them gets replaced or has an issue, then the whole file is corrupted, right? And there are other ones, other issues and stuff. But anyway, here's a third one, and this scheme uh, has like the this directory here. It has, unlike this one, what has there are three columns. This indexed one has only two columns. And this one has only one entry, but this file, cheap file that starts at 19, is actually the index block, and so you're wasting, maybe not wasting, but you're taking up a whole block to store the list of the blocks that are assigned for this file called Jeep in sequential order. So if you want to read this file, then you come to this directory and go to this index file, and then it says 9. So you go to the 9 here and read it, and then look at the next number and go to the 16 and read it and stuff like that. And then when you get to 25, and after you come back, the next number is negative number. And as I mentioned before, there is no negative number in here, so it knows that it is impossible and it just stops, right? But so that's how it works. But in terms of advantage, just like the linked one, you can use pretty efficiently whatever available free blocks wherever they are. But in terms of the waste, you are wasting, in the index here, you're wasting the whole block with that just a value. Here, usually the block is pretty large, or 120K or whatever. But you know, there'd be a good portion of this that are just a -1, right? So it is not the best use of the space. And in case that I didn't mention before, I wanted to clarify about the internal fragmentations. I think we all know about the external fragmentations, which happens between the processes or the files on the drive. But anyway, in terms of the internal fragmentation, if you are bringing a process from a file in the storage device that is a little bit larger than the RAM blocks, and only in the case where the RAM, the main storage device, is blocked off in uniform size. If this happens to be a little bit larger but less than the two of them, you will take the two of them together. But it just comes in here like this because you can't squeeze into one of them or carve it out as part of the next one because they're like units, right? So this will two blocks will be assigned for this particular block, and this is left over, and this portion of the RAM is part of this process now. Although nothing is going to be here, but this is associated with that because it took over the two. But this is still called the internal fragmentation because it's part of this one block process for this process number one. And this is sort of wasted because nothing goes in and out of there. Okay, but I just wanted to clarify that. Number two, now that we talked about how to manage a file a little bit, we can talk about how to manage the a free space, okay, free space on a storage device. And there are four methods out there, but maybe more, probably more, but there are mainly two. The first one is called the bitmap or the bit vector, and the rest of them are the variations of the length. So here, if you have well, this is a series of blocks, that can be used or empty or whatever, but you maintain a table, a small table that assigns whether the block is empty or used, right? So you can use 0 if it is already allocated, and the 0 because it's not useful for the free space. If the block is free, then you put a 1 in the in that table for that block number, then it is available, right? So that's called a bit vector or the bit map. And so this is pretty straightforward concept. It's pretty efficient, I guess. But the disadvantage of the finding a free space is you kind of have to like scan the whole thing and find out which ones are or not. Even though you assign them, you don't have to read the block. You can just look at the block ID or the indicator, right? But still, you have to kind of scan the whole thing. The linked list is, the next three of them is a variation of this, just like the files, whether it's a linked or indexed, well, specifically linked, I guess, is that you link the free blocks from the beginning to the end, right? So you can have a linked list like that, and you only have you have only one list because it'll have all the a list of files. The third one is called the grouping, and it's called grouping because it'll have a group of blocks that are available uh, in groups. Okay, so you can have three blocks, available here, 6 blocks available, whatever. In block 6, there's a three of them available there. At block 11, there's a three of them available there, and kind of like that, right? So, and then there's a counting similar to the block, but it'll tell you how many contiguous free blocks there are at a particular block. So it says block 3, there's a 4 of them, right? 1, 2, 3, 4. I mean, they happen to be contiguous, but I mean, it is contiguous for this one. And then at block number 9, it says there's a continuous 6 blocks that follows. And this is sort of useful because if you need to use a continuous set of blocks, then you kind of scan through these and see how many ever you need, and it'll tell you what that is. Okay. All right, and then let's look at number 3 here for a sec. All right, so it says number 3, given a fact-based file system, the total overhead of each entry in the table is 4 bytes. Okay, which is kind of small, but whatever. Given a 100 megabyte disk, the file system is stored, so it tells you what the size of the disk is, and then the data block, each block is a 1,000 bytes or 1K. And the question is, what is the maximum size of a file? What's the biggest file that can be stored on this disk in unit of megabytes? Okay, so let me kind of show you what this means in a picture. All right, so in a storage device here, let's say hard drive, right? So here you have blocks and whatever like that, and they're telling you, well, I'm not going to put that in right now. So here, what is the largest file size here that can go into this one, 100 megabytes? Okay, we are not going to worry about a on your storage device, whether it's a hard drive or otherwise. There usually is a OS operating system here, but we're going to pretend it doesn't exist, okay? Which is not true, but for the sake of this problem, we're not going to worry about that. Okay? All right, so let's do the calculation here a little bit. So just kind of highlighting the same question so that we can organize. We're told that the total disk size is 100 megabytes. Size of each block is a 1,000 bytes. And then overhead, we're told that it's going to be 4 bytes here. The row in the table. The number of entries in the fat table that you could have is the total disk size by each block. So it'll tell you how many blocks you got, right? So it'll say this how many blocks you got, and so this could be the smallest number of files you could have. So the total and total space occupied by the table, is how many ever files or each block it is, and the overhead for each block or the file in the table, right? So it's if you multiply the two, you get zero point 0.4 times 10 to the megabytes. Okay, so that's how much the total space occupied by the FAT. But we're asked to find the maximum file size. Okay, so if the maximum size we're told is 100 megabytes, then you have to subtract the overhead for that the table, okay, by the number of entries, and you get only 99.6 megabytes, and the cost of that overhead is 400K. So is this pretty good? I guess it's pretty good. I mean, 400K is pretty much nothing nowadays, and no one really has 100 megabytes as a storage device. So, but as you can see, it does cost something to store the files in your storage device. So let's look at the next one here. Oops. Number 4. We're told that file system has a 300 gigabytes. That's more like it. And we're going to be using what's called a file descriptor data structure um, um, scheme. And it gives us some details about how that is organized. 8 direct block addresses, 1 indirect block, 1 double indirect. And I'll tell you what they are. The size of each block, though, is 128 bytes, which is really small. But we're told that's what it is. And the size of each block, disk block address, that address it is going to use to refer to this is 8 bytes. Okay, which is also kind of small, but I think it's an easy number. What's the question? The question is what is the maximum file size that we can store in this system? Okay, so what's the biggest file we can store? Pretty much the same question from the previous one. Let's kind of look at this in terms of calculation here. So the file descriptor that he's talking about is actually called the inode structure. This is a Unix take on the file structure, and the file table looks kind of like this. It has some other kinds of information on there, but basically there is a portion in here that points to the actual data. But instead of only one, which is the direct block, sort of the fat table that we saw before, but there are other pointers, and they're called a single, double, or triple. That is called them because the direct blocks has the set of pointers or addresses to the data directly, right? Which is what we expect. But if you have only a limited number of those addresses assigned to the direct blocks, then you might run out of those addresses to point to the data files. So what you can do is you can create another table, block table, and like one address would point to this table here, and this table could have 1632 or whatever more addresses or pointers, so that they could point to the data here. So you're kind of like splitting it, right? And then the double one would be create a table here, kind of like the single one, but then instead of pointing directly to the data as in here, you point to another created table, and then you would split them off. So you can kind of like expanding it sort of exponentially here, right? In this way, you'll have a lot of pointers to the data, especially if the data is kind of small and there are many, right? So that's what they're talking about in terms of the direct and indirects, okay? But in terms of calculations, let's take a look at it. So we're told these things here. I've highlighted them before. Size of each block is 128, we're told, and each block is address or the overhead is 8 bytes, and the number of addresses that can be stored in a block is similar to the other question. But the disk block size is 128, and the address size is 8 bytes. If you divide them together, you get 16. So what this 16 means is that here these blocks are has a 16 addresses or pointers, okay? Because here it would have been better if it had 16, but we're told that we only had I think what is that? 8 direct, right? But the subsequent one will have 16. But anyway, so the maximum file size is you add up all those things: 8 direct block addresses, 1 indirect block addresses, and the size for the 1 doubly indirect block addresses, right? So the direct has 8 of them, but each block is only not only, but each block is 128 bytes, and so you multiply and add them together. The single one will have, there are 16 of them of this blocks here, so you multiply that. The one double direct is you got one of these, but each one of them will have one of these, so you multiply that and each block, and then if you add them all up together, you get 35 kilobytes. Okay, so that's how you do um, the calculations. All right, number 5. So here's a file system similar as before, but it has a one level directory structure which is implemented on the disk with a block size of 4 kilobytes. And the disk is used as the following. Uh, what is a one level? I guess these are just my notes. But anyway, so it'll look kind of like this. There will be only one. There's no, uh, there's not a single direct or double direct, kind of like that. Okay, so let me get back up there. So it'll just have one layer that points directly to the files. Okay, in that direct one. Okay, and then disk block 0. It tells you that consisting of 8-bit entry data block, right? And then block 1 has a directory with 32-bit entry per file. And then it's the same, similar question, I guess it was same here. What's the maximum possible number of files? How many files can you put it in, right? And then the second one, I think I'm going to be asking, what's the maximum file? So what's the biggest file size you can put in that the system, right? So let's do that. So let's organize this here a little bit. Size of each block is, we're told, 4 kilobytes. Okay, here, and then, and so, but we have the size of entry in the directory is 32 bits. So if you want to find out the maximum number of files, then you divide the disk block size by the each entry, the overhead, 32 bits. And so you will be able to have 1024 number of files in the system. And this is really low number, I mean, this is accurate number, but it's kind of low number because, you want to be able to store lots of files. I think most people have way more than 1,000 files. But anyway, this is how you do the calculations. And for the the other question, what is the maximum possible file size on a block? What's the is that we need to find out. Let's see here. We're told somewhere here in this table consisting of one 8-bit entry per data block, right? So we can use that 8 to figure out the maximum file size, which is 2 to the 8th or 256. Okay, I think I didn't record that one. So this will tell you how many blocks you can have, and so if each block is 4K and you multiply those two together, then you can have the biggest file you can put it together, which is about 1 gigabyte. Okay, so that's how you do the calculations for the maximum file size. The biggest file you can put. I will record the remaining questions 6 and 7 for the next lecture. Um, so in conclusion, or wrapping it up, this was a lecture video for CS350 Section 6 operating system, week number 12, Wednesday. Today I went over the file worksheet, questions 1 through 5 out of the 7 questions. Next week, next time, I will cover or finish off the the worksheet, and then I'll do the file lab. Thanks for watching. If you have any questions, feel free to email me and refer to the Blackboard. Thank you. Bye bye.